Welcome to the Department of Engineering Physics at the University of Wisconsin-Madison. I am Professor Carl Sovanek, and this presentation will introduce you to plasma and fusion research in the department and to my colleagues who lead this work. Let's start by meeting the plasma and fusion faculty of engineering physics. From the left, Assistant Professor Stephanie Diem leads experimental research in magnetic confinement. Assistant Professor Benedict Geiger investigates particle and energy transport in magnetized plasma. Professor Chris Hegna applies analytical theory to laboratory plasma configurations. Professor Oliver Schmitz studies edge plasma and plasma material interaction in magnetic confinement systems. That is me next to Professor Schmitz, and I apply numerical computation to study magnetized plasma. Professor Paul Wilson on the right is our department chair, and his neutronics applications include fusion engineering. Also, Dr. George McKee is a senior plasma scientist, and Professor Douglas Henderson's neutronics work contributes to fusion technology. The following slides will overview the active plasma and fusion research projects that are conducted by this group. But we also have the benefit of contributions from retired faculty members, Professors Emeritus Blanchard, Callan, Fonck, Kolsinski, and Moses. The Pegasus toroidal experiment is the world's smallest aspect ratio tokamak, and it is one of 3 major fusion plasma experiments on campus. Pegasus was developed and led for many years by Professor Emeritus Fonck and is now under Professor Diem's leadership. The focus of current research is plasma startup methods for spherical tokamaks, and a major upgrade is underway. The Pegasus 3 facility will be a national facility to investigate startup and current drive via helicity injection, poloidal field induction, and radio frequency waves, all while operating without conventional transformer action. Besides non-inductive startup, Pegasus has already contributed to record normalized pressure, or plasma beta, operation for tokamaks and to unique high confinement mode operation. The Maria experiment is Professor Schmitz's local plasma research facility. Like Pegasus, it is located in our building, the Engineering Research Building. It is a flexible facility for both basic plasma science and plasma technology. Its development contributes to technology for studying plasma material interaction. The configuration is also being used to develop a target plasma for laser wake field acceleration of energetic particles. In addition, this local facility provides Professor Schmitz's students with laboratory plasma experience prior to work on remote facilities, which are a large part of Professor Schmitz's research portfolio. He has active research collaborations with several national and international facilities, including the new Wendelstein 7X stellarator of the Max Planck Institute for Plasma Physics in Germany. The EDGE plasma studies investigate magnetic topology, plasma surface interaction, and plasma detachment. This effort has recently led to operation with a 10 times reduction in heat flux to what are called diverter surfaces. Maintaining relatively low heat flux to material surfaces is critical for the development of any magnetic confinement system. Professor Schmitz has both scientific staff and graduate students who work remotely at W7X and at other facilities. This provides exciting opportunities for his students. Professor Geiger also works with both remote and local plasma research facilities. His work investigates turbulent and neoclassical transport using special experimental techniques and modern spectroscopic methods. His group also develops models to describe and understand the results of the experimental analysis. Besides the W7X experiment, Professor Geiger works on the helically symmetric experiment with our colleagues in the Electrical and Computer Engineering department. Turning to theoretical work, Professor Hegna is the director of the Center for Plasma Theory and Computation. His current research activities range from the macroscopic stability of tokamaks and stellarators, to optimization of stellarator confinement, to microscale turbulence in 3D configurations, and to modeling for plasma edge and divertor physics. The highlight here notes a particularly exciting area where Professor Hegna and Professor Paul-Terry of physics and their groups are using theoretical results on turbulent transport in 3D configurations to optimize stellarator magnetic field with respect to energy confinement. The plots are from gyrokinetic modeling by postdoctoral associate Ben Faber. They show the different energy transport channels in wave number space that occur in different stellarator configurations. My own work focuses on the macroscale stability of magnetic confinement configurations and the nonlinear dynamics that result from instability. In some cases, such as tokamak disruption, the nonlinear behavior has bad consequences, and we are trying to understand its evolution sufficiently well to engineer robust solutions. In other cases, the nonlinear behavior leads to beneficial effects, such as the magnetic relaxation that changes local helicity injection in Pegasus from helical current streams into diffuse tokamak-like configurations. My group's research activities range from theoretical modeling to numerical analysis to computational implementation to physics studies achieved by applying computation. Returning to the laboratory, Dr. George McKee leads a team of scientists and students on analysis of turbulent transport in the D3D tokamak at General Atomics in San Diego and in the NSTXU experiment at the Princeton Plasma Physics Laboratory. His research includes developing novel diagnostics, investigating the correlations that lead to net transport from plasma fluctuations, and applying these results to improve plasma performance. The analysis actually allows you to visualize the collective effects that take place in turbulent plasma fluctuations. Speaking for all of the plasma and fusion research activity at Wisconsin, we have a very strong tradition in collaboration. Some of the collaborations with national groups, such as McKee's, and with international groups, such as Schmitz's and Geiger's, have been noted, but there are many more. The collaborations include theoretical and computational modeling of these experiments and participating in national and international computational teamwork. Finally, there are many collaborations across the Wisconsin academic departments that conduct plasma research. Our department, Engineering Physics, the Physics Department, Electrical and Computer Engineering, and Astronomy. In fact, it is not uncommon for plasma students in one academic program to be advised by a faculty member in another. To close, I'll leave you with links to find more information about research and graduate academics in the Engineering Physics Department at the University of Wisconsin-Madison. I wish you success in your graduate school applications and during your graduate studies.